So now I'm going to introduce for you the column vector notation. Basically, in any vector space, suppose I have a basis. So I have a vector space V, and I have chosen a set of basis vectors, and these basis vectors, let me refer to them as 1, 2, 3. I mean, there's some labels, no? Instead of writing V1, V2, V3, I'm getting lazy. I'm just calling them 1, 2, 3, n. And then any vector V, I can express as a sum ai I. Not 0. A is 1, 2. So this is going to be some a1 times basis vector 1, a2 times basis vector 2, and so on. So this is my vector. So then it is convenient to write this vector v just as its components. So a1, a2, and so on, an. I mean, this is what we do, right? You take any ijk vector and then you just pull out the components and write it as a so you might be used to seeing this, no? If I write v as 2i minus j plus 2k, then you might be tempted to represent this as 2 minus 1, 2. So what you're doing over there is you're just taking the components and putting them together in some sort of an ordered set. Same thing we're doing over here. We're taking the components a1, a2 up to an and putting them in a column matrix. So this is called the column vector notation. And it's very useful. This is what we will be using very often in quantum mechanics. So when you started out looking at vectors, you were constantly thinking of them in terms of something that has a magnitude and direction. So you were thinking of it as an object with an arrow sitting on its head. And in R2 or R3, you saw it as an arrow with some length and pointing in some orientation, some direction. Now you should start thinking about vectors in this column vector notation. So you should think of it at the back of your mind. There is some basis set. In terms of that basis, you are just treating a vector as a column with its components. So let's get a little bit of practice with this notation. Suppose I give you some sets. I want you to tell me whether these sets of vectors are linearly independent and whether they span the vector space. So the question is, are these sets of vectors in the vector space R3 linearly independent, and do they span the entire vector space? Do they span the space? So let's take the first set, just ijk, but we are going to use the column vector notation. So this is just I is just 1, 0, 0 because it's the I component of I is 1 and the j and k components of I are 0. Similarly, j is 0, 1, 0 and k is 0, 0, 1. Are these three linearly independent? Yes, they are linearly independent because you cannot write any one of them in terms of the others. Do they span R3? Yes, they do, because you take any vector in R3, you can write it in terms of these. So this is Li and this set spans R3. Okay, good. Let me take one more set. What if I take 1, 1, 0 1 0 1 0 1 1. Are these linearly independent? I want you to work it out, check it yourself, and show that they are linearly independent. And do they span all vectors in R3? How will you check that? You take in general any vector A, B, C in R3, and you want to be able to write it in terms of some A1 times the first basis vector, A2 times the second basis vector, A3 times the third basis vector. So you want to find A1, A2, A3. So you'll get 3 equations in 3 unknowns. You see if you can find a solution for A1, A2, A3. If a solution exists, then that means any vector ABC you can write in terms of these 3 basis vectors. So you will have proved that that these 3 basis vectors, they indeed do span R3. What if I take this set of vectors 1 0 0 and 0 1 0? Is this set linearly independent? Yes, because you cannot write 1 0 0 in terms of 0 1 0 or vice versa. So this is linearly independent. Does it span R3? No, it doesn't. Because as you can see, there is no z component anywhere. So if there is a vector which has a non-zero z component, you are not going to be able to express it in terms of these two vectors. So these vectors, they do not span R3. What if I take the vectors 1 0 0 0 1 0 0 0 1 1 1 0? Are these linearly independent? No, because it's possible to write this last one in terms of the first two. It's just the sum of these two. So this set of vectors is not linearly independent. Do these vectors span R3? Yes, they do, because any vector you can write in terms of these. You can write them in fact just in terms of the first 3 vectors. You don't even need the 4th vector. But in general, you can take all 4 of these and you can write any vector in terms of them. So these vectors do span R3. And what if I take 1 0 1 1 1 0 and let's say 2 1 1? Are these linearly independent? No, because the third one is again a linear combination of the first two. It's just the sum of v1 and v2. So this set of vectors is not linearly independent. Does it span R3? No, it doesn't, because not all vectors you can express in terms of these. For instance, and work it out for yourself, if you take the vector 0 1 1, you cannot express it in terms of the given 3 vectors. So if you try to write this 0 1 1 as a1 times the first one plus a2 times the second one plus a3 times the third one. Now you try to solve the 3 equations you have to get a1, a2, a3. You will find that there isn't a solution to these 3 equations. So therefore, this set of vectors these vectors do not span R3. So just some practice with the column vector notation as well as some practice with the notion of linear independence and spanning and basis vectors. Okay, to end this particular lecture, I want to again go back to the set of functions that I was talking about. So basis for the set of functions for the vector space of functions defined over the interval 0, L. Okay. So again 0 to L, and in general some function over this. I want to find out what is a good set of basis vectors in terms of which I can write all of these functions. Should be a little careful, they're not all functions. I'm specifically talking about continuous differentiable functions, but okay, for all functions of physical interest at least. Now you have studied at some point the Fourier series, right? So on this interval 0 to L, you can write a function f of x as some constant a0 plus a1 cos was it n pi x by L? So cos pi x by L plus a2 cos 2 pi x by L, and so on. In general, an cos n pi x by L. And similarly sines also, b1 sine pi x by L plus b2 sine 2 pi x by L. In general, bn sine n pi x by L. One second, let me just verify if it is n pi x by L or 2n pi x by L. Yeah, I should put 2's everywhere. 2 pi x by L, 2 times 2 pi x by L, 2 times n pi x by L. 2, 2, 2. So over here, basically what you're doing is you've written your function f, which is the vector in your vector space, in terms of these basis vectors. So here the basis is all of these cosines and all of these sines, and of course over here also 1. The basis set is 1 cos 2 pi x by L cos 4 pi x by L cos 2n pi x by L, and then also all the sines. So these are your basis vectors, and the components are a0, a1, a2, an, b1, b2, bn. And of course, this is an infinite series, which means there are an infinite number of basis vectors. So the set of functions is actually an infinite dimensional vector space. So far, when you're doing the column notation, you always think of it as having finite dimension, but that's not necessarily the case. A vector space can also be infinite dimensional, such as the set of these functions on 0, L that we're talking about. Most of the results that we will talk about, so intuitively we will always think of it in terms of the finite dimensional vector space. Most of the results will also work for infinite dimensional vector space. Sometimes we have to be a little careful that we will bring it up as and when the need for that arises. But in general, in quantum mechanics, we will often have to deal with also these infinite dimensional vector spaces. Okay, so this is all that I wanted to talk in the first lecture. In the next class, we will start talking about inner products. So notice, so far we have only been talking when we discussed the properties of vectors, we saw how to add two vectors. We didn't talk about subtraction of vectors, but we talked about the additive inverse. So when you add the additive inverse, then essentially you're subtracting a vector. And we spoke about how to multiply a scalar with a vector. So in R3, you do it component wise. But we have not discussed at any point a multiplication of two vectors. How do you multiply two vectors? Now you are used to seeing things like dot product, cross product. So we need to generalize that notion over here. So we will talk about inner products, which is a more generalized version of the dot product. And that's the topic for the next set of lectures. Okay, so we stop here.